Recently, an Airbus A320 operated by JetBlue experienced a sudden loss in altitude on a flight from Cancun to Newark, New Jersey, resulting in multiple injuries to passengers. As a result of this, Airbus grounded their entire fleet of A320s. The problem was eventually isolated to the elevator aileron computer, or ELAC, which controls the maneuvering of the plane while in flight. It turns out that a recent software update made this system susceptible to problems resulting from solar radiation. And for the most part, this could be fixed with another software change. So I know I had a lot of questions about how radiation could make this happen, and I'm sure I'm not alone. First of all, how could solar radiation cause a plane to lose that much altitude mid-flight, and what does a software fix have to do with it? And you might also be asking yourself what a nuclear engineer knows about this. Well, let's find out the answers to all of those questions. First of all, how can solar radiation cause a problem like this? Well, there are a few things that can happen here, and it really has to do with how radiation can affect electronic systems on an airplane. A modern airplane relies on a significant amount of electronics to properly operate. There are sensors all over the plane sending data to computers that are continuously monitoring and providing input to the software programs that run all the systems on the plane. This is also providing data to the pilots and the autopilot as the plane flies, and this data is used to adjust the flight parameters of the plane. It's extremely complicated, and there are multiple ways that solar radiation can impact and affect these data acquisition systems and control functions. One thing that solar radiation can do is something called a bit flip. This is a situation where a piece of data actually changes from 1 to 0 or 0 to 1 depending on what you're talking about. And this can occur when a high energy particle strikes a microprocessor or semiconductor-based memory, and it causes a change in state of that data due to an ionization effect of the component. Now, I'm sure this is an oversimplification, but essentially enough energy is transferred on the molecular level that it strips the electrons off the molecules or the atoms, and it causes an ionizing event of the component. And this can result in bad data, leading to incorrect calculations and incorrect software-driven controls or responses. This type of event is referred to as a single event upset. Essentially, you get one bad piece of data. Another way that radiation can negatively affect electronics is called a single event transient. When a high energy particle like a neutron or a proton impacts certain electronic devices, it can actually damage components. Additionally, gamma rays can strip the molecules from the air around these components and cause local ionization events. These interactions can cause a voltage pulse or other problems, including degraded performance of components, corrupted data, spiking of data that could cause erroneous indications or result in bad control functions from the computer systems that are operating the plane. Or radiation could cause a problem where a component just stops operating for a period of time. So if this is possible, why doesn't this happen on the ground? Well, it does. It just doesn't happen as much. It just happens more at altitude because there's an increased amount of solar radiation the higher up you are from the ground. Now, the Earth is being constantly bombarded by cosmic radiation. In general, this is generated from galactic phenomena like supernovas, or more locally, solar radiation generated by our sun. On the ground, we're protected from most of this radiation by the atmosphere. But at the altitude that a plane flies, there's just less atmospheric protection for the plane. So planes are just exposed to more radiation, and are therefore more likely to undergo problems like what we're talking about. And if you're curious about how much radiation a passenger in an airplane gets compared to somebody on the ground, I did a video on this recently, so check it out. So I know all of this sounds kind of scary. So what do we do about it? Well, there are a few ways that we can reduce the risk of this radiation effect on electronics on airplanes. One, we can do what's called data limiting. The engineers can set limits in the software as to what data it should consider to be a valid input. This will at least minimize the effect that an impossible piece of data could have on the control functions on the airplane. For example, you can set an upper or lower limit for temperature sensors so that impossible numbers don't end up in the control algorithms. It's not going to calculate something based on 5,000 degrees. This doesn't completely solve the problem because the data is still incorrect, but it does make the reaction to bad data less severe. Second, we can use redundancy. We can have redundant processors, redundant sensors, redundant places where we store data, all in an effect to minimize the impact that this bad data could have on operating the plane. So for example, the angle of attack sensors on an airplane are very important. Autopilots rely on these sensors to ensure a smooth and controlled flight, to prevent or recover from a stall situation. Essentially, they help the system know where the plane is in a three-dimensional space. So if you only had one of these, a bad piece of data can cause a really big problem because that's all the system knows. So you could put two of them and that puts some sort of limit on the angle that they can read. And maybe you could even average the data between the two sensors so that a bad reading isn't as bad as it would be if it was just one sensor. But this doesn't satisfy the nuclear engineer in me. So I would want 3 sensors, and I'm pretty sure that's what they do on most modern planes. That way, if you get bad data from one sensor, it's obvious which data is bad because you have 2 other sensors working properly that you can check the data against. You can do the same thing with how data is written. The odds of two components being negatively impacted at the same time in the same way is very low. So this type of redundancy really gives you a good guarantee that the data you're using is good, true data. And a third way to protect electronics from radiation is some sort of shielding. Now, this can be a little hard on an airplane. Shielding can get heavy or take up space. Airplanes don't like either of those things. So you're really only going to shield probably the most sensitive devices, and you're going to use other methods to mitigate against the impact of radiation on these components. And as I said earlier, you might be wondering why a nuclear engineer has an opinion on this. Well, a lot of this type of redundancy is analogous to how we design nuclear reactors for safe operation. The safety culture of our industries are actually very similar. Our ultimate goal is to protect the public while providing a needed service to them. Nuclear reactors are designed with redundant systems to provide backup safety features in the event of failure of components or systems, and are designed in such a way that the data that's being provided to both the operator and to the computers that are monitoring for safety can be trusted. So this is how a software upgrade can cause or fix a problem like what we saw here. There must have been something wrong in the way that the software upgrade handled data and chose which data was correct that caused this problem to happen. If I had to guess, there was probably some sort of loss in redundancy in how it handled abnormal data. As I said before, this is a very complicated system. So if there's a problem with how the software decides which data to use, this can lead to exactly what happened on this Airbus. And as I was reading about this event, I came across an incident from 2008 on a Qantas flight on another Airbus. They had a very similar problem with an in-flight loss of altitude resulting in injuries. The investigation didn't really find a smoking gun in this. It really couldn't figure out what exactly caused this bad data to cause this type of a problem. But there was a statement in the report postulating about some sort of external interference. I think it's highly likely that the same thing was going on that plane that happened on this plane here 2 months ago. And while all of this can be kind of scary, this is also an excellent example of the safety culture at Airbus. After this in-air incident, they immediately worked to figure out what was going on, and they grounded 6,000 planes during a very busy travel season. I think that's a pretty amazing response to this problem considering how many other companies respond to these types of problems. They didn't seem to care about negative press. They didn't seem to care about loss of revenue. They were focused on the safety of the passengers, which is exactly what they should be focused on. This is how all manufacturers should react when a safety concern of this magnitude arises. Anyway, I just found this to be an interesting example of a healthy safety culture. Yeah, the software upgrade did have an error in it, but once they figured it out, they did the right thing. They acted swiftly and appropriately. I am looking forward to reading the final reports on this when it's out. I'm sure it'll be interesting. But for now, the problem has been corrected and the planes have been returned to service. So this was kind of a fun one to go research. I like looking into how other industries go about solving their problems. The nuclear power industry is very focused on figuring out the causes of our problems and correcting them before they get bigger. Because when our problems get big, they get really big. It was interesting to look into how another industry really goes and looks and solves their problems and how they react to things, right? The industries are very similar in that, when we have problems, they're very public and we're very focused on our duty to protect the public. And I appreciate what these guys do and how they went and figured all this out. And I find it fascinating how similar seemingly very different technologies actually are, right? We think about things in a very similar way. We design things in a very similar way. And, ultimately our goal is on the safe operation of the thing it is we're operating and our commitment to the public to keep them safe. Ideally, so they never really even have to think about what it is we do for a living. Yeah, so this was just kind of, a fun thing to learn about. And it was nice to see a company actually act what I feel in an appropriate manner to go correct the problem they had.